Okay. Hey. Okay. Hey everyone. Today I'm going to be talking about how we represent operators that act on our big n-particle systems. We've got these many-body systems, and we want to figure out how we represent operators in terms of creation and annihilation operators to allow us to live and work in the number representation rather than the single particle basis representation, because we have all of these tensor products and it gets a little bit cumbersome. So we've got this efficient notation, but we need to transport our operators into that world. So when we were doing this in the lectures, it gets done and we get some results, but I was a bit confused about the way that we seem to get operators out of thin air a little bit, and we translated them into creation and annihilation operators, and I wasn't really sure how general these operators were, whether there was more complexity there that was sort of not being presented or not. And it turns out not really, which is nice. That there's actually a fairly simple categorization of operators that we care about. So that there are two broad classes, and pretty much all of the operators that we are going to ever care about fall into these two classes. So I'll just introduce them quickly. And basically it's simple. We've got single particle or one particle operators. That basically just go into our n-body system and figure out the property of a single particle at a time. An example of this is like the position operator or the momentum operator. These just look at single particles and encode information about single particle states. So just on notation, I'm going to put a 1, and this 1 here refers to, this is an operator that acts on a single particle Hilbert space. Single particle basis for that Hilbert space, it'll act on the basis vectors like the position basis vectors. And this exists in that one particle Hilbert space, and we'll go and extend these into the n particle system, and then we'll write that extended operator in terms of the creation and annihilation operators. So that's one class, and the other class, as you might guess, is two particle operators. And these kind of encode interactions between particles in the system. An example is the Coulomb potential operator, and that has sort of two indices. Actually, you know what? Sorry, just to be notationally consistent, we're going to call the two particle operators with a little 2 subscript here, and this takes two particles at some distant positions, and we can operate on all of the pairs of particles and find all of the energies associated with Coulomb interactions, electrostatic interactions between the particles. So yeah, these are the two broad classes, and what I'm going to do is basically extend these so that they operate on the full n-body Hilbert space, and then figure out how to represent those full extended operators in terms of creation and annihilation operators. And yeah, I'm going to prove the form for these single particle operators, and then we're going to just get this one because we're going to run out of time. And that's going to be the plan. So let's see how we go. Let's get into it. Alright, so we're going to first talk about that first class of operators, the one particle operators. And first of all, we've got to take it from the single particle Hilbert space into the n particle Hilbert space. So what we're going to write for that, if we've got some operator O, this is our big n particle one. And we're going to operate that, we're going to write it by operating it on this. Now this is one of the basis states of the n particle Hilbert space. So it's going to be a sort of tensor product of all of the single particle basis states. And to operate our operator on it, we're going to take sum over all the particles, and for each of these j indices, we're going to do the single particle, one particle operator, and you recall this subscript notation here. That's important. So that's going to be on the jth state, and this tensor product is going to go all the way up to the nth one. So obviously, as we sum through that, we've got this single particle operator operating on all of the parts of the tensor product, and that's how we extend these one particle operators out to be operating on the full n-body system. Now, the way that we're going to tackle this is we're going to think about a sort of clever choice of one of these one particle operators. Let's write it down here. It's just going to be this, where these alpha and beta are just arbitrary single particle states. So they're going to be existing in that one particle Hilbert space, because remember, this is the operator on that one particle Hilbert space. And we can see that putting this in here for all of these, we're going to come up with this. It's going to be a sum still through to n. And when it comes across this jth state, we're going to have the bj inner product come together. That's going to be a complex number, so we're going to be able to just take that out the back, and the state that's going to be left over is the alpha. So in this jth slot, we're going to have our alpha state, and it's going to carry on to the nth one, and then we're going to have our inner product of beta and phi j. And then, yeah, so that's how this single particle operator is going to operate on this, is going to kind of be extended into this n particle space. So the idea from here is that we collapse this tensor product down and just write it maybe in a more efficient form. So there's our complex numbers here, and we'll just have this alpha by n. So this is that kind of first quantization, if you like, that, you know, an in sort of a tensor product state, and we're basically figuring out how this acts on the basis vectors of the tensor product space. Okay, let's take a pause there. Okay, so I've just got this last line of where we got up to and popped it up the top here. And I'm going to rub that out, and we're going to go for a little detour into another thing, and then pick up the thread here where we got up to. So the detour is something that I didn't actually know, which is that the creation and annihilation operators have an expression in the first quantized kind of single particle basis thing. So let's look at the creation operator. This is the more simple of the two. So if we want to create a particle alpha in our n-body system, we operate it on one of the states in that system, and what it does is it basically just pops the alpha state into the tensor product. It just kind of goes in there, and that's intuitive. We've placed the state, the single particle state, into the tensor product and increased the n-body system, you know, by a particle, and it mixes up all in the tensor product. So The annihilation operator is a little bit more complicated. If we want to annihilate a particle alpha from our n-body system, then we have a sum that goes in and picks up all of the parts of alpha in this single particle, sort of in all of the single particle representations. And we get a plus and minus here. So that's the sort of component there, and it goes in, so we get k minus 1, k plus 1, and that goes all the way to the end, phi n, closes off the bracket. So it kind of goes in and finds all of the component parts of alpha and takes it out. So it's sort of taken out that part of the phi k component of alpha, and once it goes through and finds all the components of alpha and slurps them out, we're left with a state where alpha is effectively gone. And we have a few constants and things like that. In a similar way that when you operate the creation operator on the number state, you get, that number constant out the front. So these are the associated constants for that. So yeah, that's our little detour into how the creation and annihilation operators are represented when operating on the sort of first quantized notation. So we'll now pick up the thread with where we're up to. Alright, so I've set us out to try and figure out how to represent this operator in terms of creation and annihilation operators. And I've defined these creation and annihilation operators on the first quantized notation. And basically the method is going to be that I'm going to write something down, and we're going to see that when it operates on this same state, we get to this same place. And so I'm going to say that that's how we write this down. And remember that this is the extension of that single particle operator of just A and B, like ket alpha and ket beta, the single particle operator. So we've extended that into the n particle system. All right, so I'm going to write this down. I'm going to say, and it's pretty obvious, but we're going to prove it, and it wasn't proven in the lectures, and so here's kind of the proof. We're going to create an alpha, and we're going to annihilate a beta. So we're going to sort of operate that on this same state, and we're going to sort of be able to try and see some correspondence between these two things, and in fact that they're equal. So using these, let's basically just, noting that this, is exactly the same as this, we're going to write it down. So we're going to have this big sum over the k's. We're going to have our plus or minus. We're going to have the creation ones being applied to beta here. So we're going to go with beta phi k. And then we're going to have the creation alpha. So we're going to have this alpha thing in here and the rest. So phi 1. And then we've got our phi k minus 1, phi k plus 1, blah, 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 all the way down to phi n. Is it phi or psi? Should know, not sure. So this is basically just using these to operate on this. And now we're going to just take a look at this here. We're going to see that this is just a number, and if we have our symmetry or anti-symmetry, we go and move this alpha so that it's in the kth spot, in between k minus 1 and k plus 1. And because of the symmetry, well, for bosons, we don't change the sign, so it becomes plus with alpha in the kth slot. And it turns out that fermions, we do it so that it gives us a plus as well. and that's always possible. This plus or minus thing isn't strictly speaking right, but it's a bit unnecessarily complicated, so we're going to say that this goes to this, that's the k minus 1, that's the kth one, that's the k plus 1, and down to the end. And basically what we've realized here is that this has exactly the same form as this. And so this way of writing it is valid. Basically we've shown that that is found with this. And recalling again, this is the extension of this alpha beta. Cool, so just obviously we've got this big operator on the n particle system, and we can write it with this fairly simple expression of creation and annihilation operators. Alright, so we're pretty much there. We've found this operator in terms of the creation and annihilation operators, but we've recognized that it's kind of the extension of a pretty limited single particle operator. So let's use a totally general single particle operator. Let's call it G1. And we've seen this before. In some discrete basis, we've just got these set of coefficients timesing out this sort of sum of operators on each of the mn pairs. So this is a totally general operator on a single particle state, but we recognize this here, and we see that we can extend this into the n particle system as follows. Alright, so this is sort of the end point of all of this. This is the key one particle operator, which is half of all of the operators that we ever see. In this totally general form here, acting on the single particle Hilbert space, can be extended to operate on the n particle system and represented in terms of the creation and annihilation operators in any basis we care for. So we've got this discrete m, n, m basis. As this, we've got some coefficients, and we've just got the annihilating an n and creating an m. So cool, we've successfully represented any general single particle operator in this form and shown the steps of how to get there. And that's great because, you know, we can form, well, let's first just see the form of the two particle operators. I'm just going to write this down because this is a long ass video. So for some, you know, general two particle operator, this is acting on like the combined Hilbert space, so we get some some normalization thing there. And for sort of two separate particles, we'd have some operator that cares about the two different things. And in exactly the same way that we've got a general operator on the single particle states, we've got a general operator on the pairs, this sort of whatever that ends up being. And we can extend this into the n particle system as follows. Okay, so we've got this thing here. We're going to use alpha, beta, gamma, delta. And yeah, it's going to be very similar looking. Delta, we're going to have creating alpha and beta and annihilating gamma and delta. So that's kind of the equivalent thing. So these two are our main results, and we can write those down and tuck them away in our memory as representing the full span of possible operators. So all of our Hamiltonians and complicated operators are going to boil down to sums and products of either single particle operators or double particle operators, and those can all be represented as this in terms of these creation and annihilation operators. And once we've got it in that form, we've successfully moved house from first quantization into second quantization, and can live there, which is good. That's what we're after.